This problem says, find the absolute maximum and minimum of f of x equals 5 minus 6x squared minus 2x cubed on the closed interval -3 to 1. So when we're talking about absolute maximums and minimums on a closed range, let's say some function that we cared about on this interval and the function looked like this. So all we are concerned about is this region right here. So let's say that it's continuous right there. I know that looks like a point, but let's say it's not continuous there. There's a corner. Well, it's continuous, but it's not differentiable because the limit as you go this way is a slope downwards, and then suddenly, but that's getting ahead of ourselves. So by looking at this, you can tell that on this interval, the highest point it ever gets is, this value of x, call it x1. And the lowest it ever gets is this point right here, call it x2. So how do you, without having to draw a function and look at it, how do you figure out which points to check out? Well, as I said, I was looking at slopes. So you know that taking the first derivative has something to do with it. How about this? Let's say this was a maximum, because it is in this neighborhood. What is the slope right at the top? It's 0, right? Let's say this is f of x. So we can tell at a maximum, f prime of x is going to equal 0. But also, if you had another function and you wanted to know, you saw at this point, also the slope is 0. So once you find a place where the first derivative is 0, how do you tell if it's a maximum or a minimum? How about this? For points for x less than, let's call this point C. So if x is less than C, look at the slope. Is it positive or negative? It's positive. And for x greater than C, once it's reached the point where the slope is 0, then it starts going down because you're going down from the maximum. What's your slope? What's the value of the derivative for values above C in the neighborhood of C? Well, now you're going downwards, so this first derivative is negative. So look at these two things. If we found some critical point where the slope is 0, so f prime of C equals 0, it could be a maximum or it could be a minimum. In the case when it's a maximum, what is true? If we're talking about the values of x less than that critical point, then our slope is positive. And if our value of x is greater, then the slope is negative, then it's a maximum. Now, looking over here, if this point were called C, and if we found that f prime of C were equal to 0, for x less than C, for x values here, what is the slope? What is the value of the derivative function for values of x less than C in the neighborhood of C? Is it greater than 0 or less than 0? Less than 0, because it's pointing downwards. Then it gets to its lowest possible point. The slope is 0 because the tangent is a horizontal line. And then for values of x greater than C, you're on your way up. So the value of the derivative of x is greater than 0. But as I said earlier, just because you found a place where the critical point doesn't exist, the derivative doesn't exist there. If the function is continuous, it could be that this is a local maximum, or it could be a local minimum, or on that interval. So the first step for this type of problem is find the derivative function. Let's do that. This is a polynomial. We know it's continuous everywhere, and it's differentiable everywhere. So what is the derivative of 5 minus 6x squared minus 2x cubed? We can use the power rule and say that the f prime of x is equal to negative 12x minus 2 times 3 is 6 x squared. Okay. So this is the derivative. Let's simplify it. We're going to want to simplify this. We're going to factor out an x. We can also factor out a negative 6. because both of these are divisible by negative 6. So what leaves this? 2. And then minus 6 times 2 minus x. And what values of x make this equal to 0? Because for critical points, we care about where the derivative is 0, and we also want to check where the derivative is undefined. These are commonly called critical points. With this polynomial function, with its polynomial function derivative, we're not going to have any of this type, but we are going to have some zeros. And look, they're not both, because one of them is at 0, but the other one is at 2, but we are in the range from -3 to 1. So we want to care about this one. And also, because these are closed bounds, we care about the endpoints. Let's say I drew the endpoints with solid lines. And what if the function looked like this? This is a point. And if this were a point where the slope was also 0, we would want to check that. But we also want to check this and this. And we'll check this because it's a critical point. And we check this. Notice that we don't have a slope of the tangent line of 0 at these points, but they could be maxima or minima because they are the endpoints. So we only have one critical point inside the range. So we want to check at x equals 0. And we also want to check at x equals -3. And we also want to check at x equals 1. But did we forget to do something? What is this, a maximum or a minimum? How can we tell? By analysis of the derivative function. Let's say that x is slightly less than 0. Okay? If x is slightly less than 0, in the neighborhood of 0, then this would be a small negative number. -6 times a negative number would be positive, yes? And 2 minus a small negative number would be slightly more than 2, so it would be positive. So the slope of x for x slightly less than 0 would be greater than 0. How about for x slightly greater than 0? What would the slope be? Well, if x is slightly greater than 0, then it's positive. -6 times a positive number is negative. And 2 minus x, 2 minus a number slightly greater than 0 would be a positive value. Negative times a positive is a negative. So look at this. Let's say this is x equals 0. So the value of the derivative function is positive. It's pointing, the slope is pointing upwards. It gets to 0 at 0, and then it's pointing downwards. So we're talking about something like this. See how slightly less? So this is possibly a local maximum. All right. So let's plug in the values of -3, 0, and 1 in the original function and see which ones of these are the smallest and which ones of these are the largest. Let's start with -3. So we've got 5 minus 6 times -3 squared minus 2 times -3 cubed. What's -3 squared is 9. 6 times 9 is 54. 5 minus 54. Now this is -3 cubed is -27. -27. 27 times 2 is 7 times 2 is 14. 2 times 4 is 54. So -2 times -27 is positive 54. Very nice. So this is 5. So we have f of -3 equals 5. Okay. What about x equals 0? We can do that by inspection almost. 0 squared is 0. 6. So these terms go away. We're left with 5. Interesting. How about f of 1? 5 minus 6 times 1, 1 squared is 1. 5 minus 6 minus 2 times 1 is 1 cubed is 1. 5 minus 6 is negative 1. Negative 1 minus 2 equals negative 3. So what is it? Which one is the maximum? Well, there can be more than one maximum. We could say that the absolute maximum is 5, and the absolute minimum is negative 3. So the way we solved this was we found the derivative, and we found the critical points, and we calculated the value of the original function at the endpoints and the critical points inside the range. And then we found the greatest and least of those. This problem says find the critical numbers of k of z equals 4z cubed plus 5z squared minus 42z plus 7. Okay. If you rush into this problem, you might forget and think to yourself, oh, critical numbers, I got to find the zeros of this function. But no. What do you want to find the zeros of? You want to find the zeros of k prime of z, which means you got to take the derivative and then look for the roots of that. So let's do this. We'll say k prime of z equals, okay, 4z cubed. 3 times 4 is 12. Z decremented squared plus 2 times 5 is 10. Z, and then 42, negative 42z, the derivative is just 42. All right, now we have to factor this. Is this a friendly function, easy to factor? This is my technique. I know that if it is factorable, it's going to be like this. Or I got some coefficient here, z, some coefficient here. I'm going to write the factors of 12. This is the way I sometimes do it in case I can't immediately see. I know that these two have to go together, 2 and 6, 3 and 4. Now 42, let's see, we got 1 and 42. We got 2 and 21. Let's see, what are the other ones? 6 and 7. Any others? So I look at these and I say to myself, these two got to multiply out and be 12. These two got to multiply out and be 42. But as far as the first and last, the outer and inner products have to add up to 10. So let's see, what do we got here? 12, 42, well, 6 times 4 is 24, 3 times 7 is 21, no. 2, 6 is 12, 6, 7 is 42, no. How about 3? This is something best done when you're not trying to figure it out with somebody watching you. I can say that. So I made it easier for myself by factoring out a 2 here. And that left 6z squared plus 5z minus 21. And that can factor out 6 is 2 and 3. 2 times 7 is 14. 14 minus 9 is 5. So we have critical numbers at z equals, this one goes to 0 when z equals 3/2. And this one goes to 0 when z equals negative 7/3. And so this is what the problem wanted. It wanted to find out the critical numbers where the function has a maximum or a minimum. It didn't say to find out if they were maximums or minimums, just to find the critical numbers. So we took the derivative and factored it to find the zeros of the derivative. This one says, prove that a polynomial function of degree 1 has no local or absolute extrema on the interval from negative infinity to positive infinity. So we got to prove this. How do we prove something? There's the direct proof, and then there's a proof by contradiction. Can you think of a way to prove this directly? It's talking about polynomial functions of degree 1. So we could say f of x equals some ax, where a is a real number. Okay, so a is a constant real number. And what do we know about maximum or minimums, extrema? We find out where are the critical numbers. So look at this function. Where are the critical numbers? Are they there where the derivative equals 0? And we should have stated a is not equal to 0, because if a is 0, is this a first degree polynomial? No, it's just the 0 function. So now that we remember to establish that a is some real number not equal to 0, and to find the absolute extrema on a closed interval, or the local or absolute extrema, we find out where are the critical numbers. We do that by taking the derivative of the original function and setting it equal to 0. Okay, let's take the derivative of the function ax, where a is not equal to 0. This is just the value a. This is a constant function. Let's say that a was right here. Then the graph of a would just look like this. From negative infinity all the way to infinity, for every value of x, the derivative of this function is a. There's no critical number for which the derivative of this function is 0. Therefore, there are no critical numbers. Therefore, there are no local or absolute extrema on that interval.